let's take a look at one of the major segments here in California, aerospace. I'd like to introduce a speaker who is going to talk more about how to serve the digital thread, no pun intended, and especially how this applies to aerospace industry. From iBASEt, I would like to welcome Michel Gadbois.
Very good. Hello, everyone. Thank you very much, Vladimir. So let's get started. So iBase-t is a partner of Hexagon. We'll be describing to you in a few minutes what exactly we do and some of the challenges that we face in complex discrete. We're going to talk mostly about aerospace today as an example because aerostructures is something a lot of us are familiar with. But really, these challenges are going to be common to just about everyone that's in complex discrete. And by the way, when I say discrete, for those of you that are not in the discrete manufacturing industry, it doesn't mean that your products can keep a secret. It just means that you build them one at a time. So you're going to hear us use that term over and over again. And that's what it's about. So first of all, you've been walking around the zone in the last 2 days, and you've been getting exposed to a lot of Hexagon's hardware and software technology that are connected that are going to help you get real-time metrics both from a process standpoint and from a dimensional standpoint. You've also, if you've been working around this particular part in the zone, you've been looking at some tools that are able to take that data in real time and turn that into actionable intelligence. So what's left? We've talked about sensing, thinking. The part that's left is acting. And this is what we're going to be spending the next 20 minutes or so talking about, is really how do you take all that great knowledge and intelligence you've just gathered and apply that to defining and refining your process in complex discrete. So we're going to talk about Industry 4.0 or smart manufacturing. We're going to talk today about the model-based enterprise and the digital thread. There's a lot of terms here, but we'll help you define the digital thread a little bit further down into this presentation. Model-based enterprise is really the concept where we start taking all of the investment that we've made up front into our solid modeling and all of the underlying data, like the PMI data, and get that out into the manufacturing process. And we'll talk more about that as we go along. So iBase-t's role, our product is called Solumina, really plays that role surrounding acting, defining a process, executing that process, and managing all of the quality parameters and actions that go either when things go well or when things don't go so well. So let's take the sensing, thinking, and acting, and let's arrange that in a circle, because that's really what it is. I'm going to take some measurements. I'm going to use some great tools to figure out whether there's some correlation I should be reacting to. And then I'm going to need to take this data to refine the processes that I've defined. So sensing is going to come first, and then we're doing the analysis, and then we're refining. Now in our case, when we talk about acting, we're going to cover both the initial definition of what's a process and what's important, and then we're also going to talk about how do we in this continuous loop go back and make adjustments and refinements as we learn that there are things that are not going as well as we originally intended. Let's talk about the tools that are going to be part of this. So on the sensing part, there's going to be a collaboration between our work orders. Our product is called Solumina, and the real-time metrics that are going to be coming into those work order operations as the sensing equipment is doing its job and telling us whether we're staying within the control parameters or starting to stray out and need to take some preventative action. On the thinking side, we're going to use predictive analysis and process intelligence tools. For those of you who've been and looked at the QDOS tools and the MMS Connect tools, they're starting to give you some indications that things need to be adjusted or corrected, and even in some cases giving you some recommendations as to what tools to use or how to adjust the tools to get best results. On the planning side, you're going to hear us talk about process planning. A process plan in our world is really the definition of everything we need to know to execute the work precisely as we intended, both from a product and from a process perspective. A process plan is really what used to replace 6, 7, 8 different document sources in the more historical world of aerospace and complex discrete. So you're going to hear us talk a lot about that. And then of course all the quality management functionality that goes along with it. Now, if we're going to get on the digital thread, and in a second I'm going to kind of give you a good definition for that, But if we're going to start building and extending our data, we have to start with the design data. So the first thing that we had to tackle is how to get the PLM information completely integrated into this loop seamlessly. The next thing that we had to figure out is, okay, we're not alone, we're not an island. Our 6, 7, 8, or 10 facilities do not work by themselves. The reality in complex discrete is up to 80% of the value add is coming from your supply chain, from your partners. So how do we get them tied into this definition that we're building, this digital thread, so that they can participate, they can react quickly to engineering changes, and they can do their best job in giving us precisely what we wanted and when we wanted it. So once we've created this environment, we have the makings now for the digital thread. So how to define the digital thread? All of you probably are putting money away every month for a rainy day. Your 401k, for those of you in Canada, your RRSP, et cetera, et cetera. Well, imagine for a second that you put money in the 401k every quarter, and once every 6 months you took a peek at your 401k, and randomly 25% of the money was gone. You would freak out. Well, in manufacturing, believe it or not, we invest millions or billions up front in designing products and processes. We put that down into various systems. And when it comes down to going to manufacturing, a lot of that data gets thrown away, reused, reinterpreted, retyped. So we're actually taking a lot of our investment and we're throwing it away and we're starting again. Sometimes it happens well and we keep 90% of it. Sometimes we only keep 10% of it. It's not consistent. So the digital thread, if you want to look at it that way, is essentially a knowledge bank, a growing, connected, interrelated knowledge bank that's going to make sure that once you've invested in your product definition and your process definition, that data can continue to flow smoothly to all the actors that need to receive that information in an additive way. So if we want to prevent the digital thread from becoming a tangled mess, we've got to set some rules. And let's take a look at what those are. So the first rule is, in the digital thread, there must be for every data element, and there could be many actors providing data elements into the digital thread, but for every element there must be one master. We cannot have two people working on the bill of material. Once, and in our terms in aerospace, once an engineering bill of material turns into a manufacturing bill of material, that definition should be sacred until it evolves. There shouldn't be someone reinventing it or retyping it in, et cetera, et cetera. The second rule is, as this data repository grows, and in our industry, when we make aircraft and bombers and nuclear submarines and missiles, there's a lot of data. In our industry, we tend to give people too much information. Well, what happens? When you give me a 400-page document to tell me how to do something, I won't even look at it. I'll rely on my memory, because there's no way I'm going to look at 400 pages. The new generation, if we can't get what's going on in the next 3 seconds, we'll move on to the next topic. So we have to deliver just the right information, no more, no less, and that's going to help us ensure that we're delivering a quality process and we're getting precisely what we wanted. You're going to hear me talk a lot about that, asking and getting precisely what we wanted from our various assets, whether they be the supply chain or the shop floor. The third rule is, we know that in our industry, in a traceable industry, we've got to collect data. Now, strictly speaking, collecting data does not add value to the product, but it's a necessary part of knowing whether we're doing what we intended, whether we're within process parameters, and let's face it, most of our contract requirements require an entire digital twin to be delivered with the units, so we have to have that information. Not collecting data would be like driving down the highway at high speed and every single one of your windows is painted over. Could you do it? Once. You wouldn't get great results. The fourth and final rule, and this is where iBase-t and our Solumina product really makes a difference, is that if I'm going to collect data, I want that data validated now. Not an hour later, not 10 minutes later. I want that data validated now. In most aerospace companies still today, they create a digital package or a paper package made up of 7, 8, 10 disconnected systems, and at the end of the week or at the end of the unit build, there's someone that goes through all of that to verify whether the signatures were there, the data was within specs, the serial numbers were valid, none of the stamps were smudged, et cetera, et cetera. Finding out later whether your data works or not would be like driving your car again. All your windows are still painted over except for the back window. Again, could you do it? For a little while, the results would not be great. So we want to change that. We want to make sure that any data that's collected is validated in real time, so whether the tool was the right tool, it was still within calibration, the serial number had not been used before, it was the right revision of part for that serial number of aircraft or satellite, etc. So for this to work on a grand scale, for people to adopt the digital thread on a grand scale without enormous cost and effort, requires what we call APIs or connections. What we're trying to do is to change the industry so that discrete manufacturers no longer have to take the responsibility of linking their key systems together. Believe it or not, most IT groups in our industry spend up to 40% of their labor dollars keeping the systems talking to each other. It's not offered to them, they have to do it themselves, and when any one of those systems, ERP, PLM, shop floor tools, when any one of them change, they've got to then readapt the interface, retest the interface, etc. So iBase-t has basically removed that. When we deliver the product, which is sitting neatly between ERP and PLM, we deliver a standard set of catalog interfaces to your ERP and to your PLMs so that the data flows smoothly and you can get out of the interface business. If you don't do that, adopting the digital thread becomes extremely difficult and scary. So let's take all of our pieces, sensing, thinking, and acting. We're going to leave, for the rest of the presentation, PLM out of the equation because just talking about what data goes back and forth between PLM and Solumina would take an hour. So let's leave that out for now. We can do that on another session. And let's start focusing on the pieces we will cover, but let's rearrange them a little bit differently. We're going to start with acting because acting is going to be the first thing we're going to do where we're going to define our processes. We'll go back to acting over and over again as we get actionable intelligence and we start refining our process. Then we'll talk about sensing. Sensing not only from the real-time metrics and telemetry coming from the devices, but how those actually go into the process recipe and get collected as part of the as-built. And then finally, we'll talk about thinking about how we react to all this and feed now some new process changes into the loop. The example we're going to use today is Aerostructures. It's something that most of you have been exposed to. Every one of you, how many people here actually flew into this conference? A big chunk of you. So a lot of you, your lives actually relied on making sure that those Aerostructures were put together right the first time. So this is going to be meaningful to you. And I promise, nothing we're going to talk about today is going to make you not want to get on that airplane at the end of the week. So rest assured. So we'll talk about Aerostructures as an example. It's a good example that has most of the challenges we faced in complex discrete. But really, these rules and these challenges apply to most people that make complicated things. So what are some of the challenges that we face in complex discrete? Enormous structures, 3.5, 4.5 million parts that all have to come together in a particular sequence and get delivered. Very daunting. The lead times on the material, a lead time is how long it takes from the time I figure out I need something to the time I have it sitting in my dock or my point of use. Lead times in complex discrete can be extremely long. Specific heats of material with specific properties have to be certified, and they get pointed to a specific program or contract, so you can't just use them as you see fit. You may have 3 bars of 17.4 pH stainless steel, but this one's for this program, this one's for this customer, and this one's for this contract. That's just the way it has to work in the environment. So your hands are tied. The volumes are so low in this industry that you cannot engineer out the variability. In automotive, one of the wonderful advantages that we have is that we can basically define a process. We're going to run through it as many times as we need to, but once we have a good process, we're going to make 10,000 of something. So Murphy, for those of you that are old enough to remember Murphy, may not be completely gone from the shop floor, but Murphy is not CEO. In aerospace, because the volumes are so low, we never have a chance of engineering out all variability. So the important thing is to try to remove whatever variation or variability or unpredictability we can. The design cycles are extremely quick and they change extremely quickly. We have customers that make products that from the time the beginning of the product is started to the time that unit is going to be delivered, that particular unit has gone through hundreds of engineering changes. And I'm not talking about the model going through hundreds of changes. That unit, that tail number, that submarine, that satellite was touched and rethought and redefined 100 times. I'm told that an aircraft carrier, by the time it leaves the dock, the entire electronic suite has been designed, installed, tested, removed, reinstalled, and retested 7 times, because the design changes faster than we can build the aircraft carrier. So think about that. The lead times associated for change are in days. I may be cutting a work order on the shop floor with half of the operations not even written yet, and I'll be writing the rest as I go along. Completely unknown in any other industry. And then finally, the traceability and genealogy requirements are extremely high. You have to deliver this traceability with each unit, and it must be perfect. So let's talk about some of the tools that we're going to be going over today. So on the acting side, you're going to hear us talk about process definition or process planning. This is where we're going to take from a legacy environment some data collection sheets, ERP routing sheets, work instructions in various form, SPC tools. We're going to merge all of that into one consolidated document we call a process plan. On the sensing side, we're going to take a twin of that process plan for every unit, but that unit is going to be a little bit different than the other units. It'll adapt. Its structure will change. We call that unit effectivity. But its structure will change depending on who we're building that unit for. And now that work order is going to be waiting for people and for machines to provide us real-time feedback so that we know that we're doing things in the right sequence and the right way. And then, of course, our analytics tools are constantly working to give us the feedback that we need to know whether we're trending out of control in any particular area. And of course, the moment we think we have all of this straight, PLM sends us a message, there's been an engineering change, or customer wanted a new option, and the process now has to adapt. So this never ends. So let's talk about process planning, the definition, the beginning of acting in this particular scene. So the challenges we have in process planning is that we must have very strict sequence control. You have to do things when you're building an airplane or a satellite. You have to build things in a very particular sequence, and you have to test them and power them up in a very particular sequence. But because you're going to have multiple part shortages, you're going to have tool issues, and you're going to have design changes, you're going to need to adapt that sequence on the fly. So you've got to be able to define a way to get the work done the way you ideally would like it to get it done, but yet react very quickly when things change. The next thing is that you've got now composites in the picture. How many people here come from an environment where you do composites, carbon fiber? Okay, a few. So let's talk composites. Composites have completely revolutionized aerostructures. They're wonderful. You can do bigger, larger pieces, lighter, greater strength for weight, all of those things. But with composites comes a whole series of process control issues that you have to keep control of. So you've got you've got void detection, porosity detection, delamination issues that may happen if you improperly drill. You've got out time, for those of you that you've probably never heard of out time. But when you work with composites, the moment you take them out of the freezer, they have to get to layup, and they have to get to the autoclave, which is a big vacuum oven for curing, within a certain time. And if you can't do that, you will not be able to certify the strength of the composite. So all of that now is adding complexity in our process definition and our execution to make sure you do, again, precisely what you intended to do. Torque requirements have always been an issue in complex discrete, both from a perspective of sequence and the spec of the torque, whether it be in degrees or foot-pounds. But now with composites, torque has become even more important. Composites are great as long as you don't abuse them. If you abuse them, now they start to behave in really unflattering ways. The PLM is going to continue as we go down the digital thread to play an extremely important role in feeding the digital thread. Let me give you just one statistic that goes along with that. We took a hybrid of the F-35 program, which is our new Joint Strike Fighter, and the Virginia-class submarine, and we mushed them together to protect the innocent. And we said, what does it cost through the life of the program to define all the visuals for all the process steps through manufacturing and assembly if we didn't use the PLM, if we basically reinvented after the PLM, which is, by the way, what most people still do today. We calculated that through the life of the program, there's $850 million being spent creating, adjusting, inserting, reacting to the visual updates, just the visuals. We're not talking bills of materials, we're not talking SPC, we're talking just creating the pictures that people use as they build and repair those units. Enormous amount of money. So process plans now, great, we've created this great process definition for the shop floor. How do I get that same level of definition for my partners in the supply chain? How do I tell them what they need to build? How do I show them quickly when there's an engineering change? How do I ensure that they did precisely what they were supposed to do before they shipped the parts? For those of you that are in complex manufacturing, you probably know the days where you get something in receiving and it's not at all what it was supposed to be. And now some program, some aircraft is going to be delayed by 3 months while the vendor reacts to it. So what you're left with is a single clean user interface that defines everything that needs to happen and all the data that needs to come in. And it is even intelligent enough to know that Mary and Bob are both working on this process. Mary, the last time she did one of those, it was exactly like this one, no issues. Bob, it was 2 weeks before, and when Bob did it, the process wasn't the same. So it alerts Bob that there's been a change, and Bob, here's what's changed since you last did this. Because like it or not, our people are going to use their memory to assemble and manufacture, and that can lead them astray. So just to give you an example of the value of that, C-17, when they built their first 120 aircraft, estimated by using Solumina and the integration that came with, they saved $120 million over the first 120 aircraft, 125 actually. Huge money. So assignment. So we've talked about the fact that we're now going to take a twin of this definition. We're going to release it for the people that have to do the work. And as we need, we're going to collect the values, signatures. We're going to get all of this metrology from the hexagon tools coming straight in and giving us our pass-fail values. And the process goes on. The key here is catching the issues at the right time so that we can react to them. We have customers where one piece of work in process, for those of you that saw, who saw the SpaceX launch this morning? Not too many. There was a launch this morning. So if you just take one part of that engine and you look at how much dollars goes into that one piece of metal before it gets finished, it can go up to $100,000. Imagine if some poor person at the end of that process is the one who messes it up and scraps it. That's career ending. So what we've got to do in this industry is we've got to make sure that people do precisely what they're supposed to in the sequence that they're supposed to. And it looks like if there's any evidence that seems to point that they're trending out of control, they're not even out of spec yet. Stop, make an adjustment, and improve. And that's the capability that these integrated tools bring to the picture. So what you're left with is a suite of integrated pieces of information that connect the design engineer, the process engineer, the technician, and the customer. In the case of many of our customers, many of our products, customers' products, are actually overseen by the people that ultimately buy them. So they're in your factory, they're signing off, they're making changes. So we wanted to come up with a whole suite of collaborative tools to make sure that everyone is on the same picture. Let's take one example of how all of that comes together to really change your environment. For those of you that remember the space shuttle, Atlantis STS-115 was one of its last missions, and they discovered, after it was already on the launch pad, that one of the Ka band antenna bolts, or two actually of them, were the wrong length. They were about 2 threads too short. Had they not had the integrated suite of tools that Solumina provided, they would have, in the old way, would have had to basically defuel the stack because they would have missed their launch window, gone through the whole process. They estimated that in the old days it would have taken them about 2.5 weeks to go through the process of identifying what was wrong, figuring out what to do about it, getting the proper signatures, and getting the change done. 2.5 weeks meant no launch window. No launch window meant take all the fuel out, take everybody away, you've got to start the process over again. That one event, but because of Solumina, they were able to do all of this in 2.5 days. The process was approved, signed off interactively. They were looking at pictures and making sure they were doing the right thing, and we kept our launch window. That one event alone, NASA says, saved them upward of $15 million by keeping their launch window. One event, $15 million. Let's talk about another interesting fact in our industry. In our industry, we found out that up to 20% of defects, we live in an industry because the variability is so high, there's a lot of things that go wrong. And we found that up to 20% of the defects are paperwork defects. Somebody put in a number that you couldn't read. Somebody used a serial number that had been used before. Someone's stamp couldn't be read. The interesting fact is that fixing those paperwork defects is 80% the cost of a regular defect because it means tear down, reinspection, reassembly, and everything that goes along with it. Extremely expensive. So all of this to say, we've got to switch the paradigm, leverage what we have on the digital thread, and we've got to validate every piece of data that we collect in real time, not the week after. Let's get back to our supply chain for a second. Our suppliers do 80% of our value add. They are probably the most critical piece of our entire value chain. Most of you probably have stories where you weren't able to deliver products, not because of something you did on the shop floor, but because one of your suppliers wasn't able to help you out. So the suppliers today, most of them are still being communicated to with emails and Excel spreadsheets. You've heard of the expression MES, multiple Excel spreadsheets. That's a lot of people's systems today. These papers are being filled out by interns. Interesting statistic, if you didn't know this, on the supplier side, they get less than 10%, the process engineering and engineering support per value-added dollar that we give our own resources. They're our most critical resource, and yet they get the least amount of attention. So how do we bring the suppliers in? How do we make sure that they're doing their first articles properly? How do they get instant notification of an engineering change? How do we make sure if we have an issue on the shop floor that nanoseconds later they can see their part, see the digital defect, see the photos, and you're already working together on the next generation? How do we get them dialed into the digital thread? That's what Solumina does. And then, we talked about this. So let's take an example. One example from one of our customers where they've taken their supply chain and they've linked it into the digital thread. So this is a little bit of a depressing example, but it gives you an idea of just how much potential is out there. So this one customer, before they started this digital thread initiative with their supply chain, had 45 people in receiving inspection. These are just people inspecting the incoming products. They had so much backlog that on average, from the time something arrived at the receiving dock to the time it was brought to point of use was 90 days. 90 days. It was so long that the CFO had no choice but to pay vendors sight unseen for their products, even though they hadn't been inspected. Because I'm not going to have my partners wait for 3 months to get paid. So try getting your money back when you find out that you didn't get what you were expecting. Not an easy task. $2.5 million a year were being spent for contract inspectors. For those of you that know supplier quality, these are the poor souls that have to go into those vendors' facilities. They're not, they're about as popular as the IRS, just to give you a feel. But these poor souls have to go into those vendors' facilities and say, I represent manufacturer A. We'd like to make sure you're doing things right. So they were spending $2.5 million of contract inspectors to try to keep their key vendors in line. There was enormous amount of escapes, even with all of that vendor inspection and those audits. Lots of shortages, lots of parts stuck in receiving inspection that was causing aircraft to not be delivered on time. So a pretty bad mess. Now, after we implemented this technology, 9 people in receiving inspection instead of 45. Most goods through receiving inspection, straight to point of use, either immediately or within a week. Because really we put all the burden of inspection and verification at the source, at the supplier site. They were delegated quality representatives. They knew what they were doing. That stuff could flow automatically. And when they had a problem, they were electronically linked into our database. So we saw their defect. We reviewed in real time what was happening. So we knew before those goods even arrived in receiving that they were good to go. We went from $2.5 million of contract inspectors to $500,000, but here's the catch. That $500,000 we didn't pay for. We basically had an agreement with our suppliers. We're going to give you all the tools and all the visibility you ever dreamed of, but if you still can't keep your quality level to X, from a DPPM standpoint, defects per million, we're going to send the inspectors back, but now you're paying for them, not us. So that $500,000 we're not even paying for. 95% of defects are caught at the source and dealt with before we ever see the parts. Most of the parts received go straight to point of use because they've been pre-verified. The only time, in fact, in receiving inspection that will stop something is if we did what we call an over-inspection or an audit. And all the data now with the vendor is electronic. From them sending us their certificates of compliance and their certs and reps, from us sending them 3D models of what's changed and getting a handshake on the process, all done electronically. So we have about 3,500 suppliers in one site alone, 5,000 if you look at all of our customers, that are connecting every week to this portal, to these portal pages, and we collect almost 1 million transactions a month. So in conclusion, complex discrete manufacturers, Aerostructures, medical devices, industrial equipment, we all have the same issues. It is what we call the perfect storm of issues. Very complex processes and structures, very little time to engineer out the variability, lots of change, and customers and design agencies that that don't know from minute A to minute B what exactly they want and what's going to need to be done. So dealing with this triangle of unpredictability means that we have to basically look at every place where we can cheat Murphy, if you will, and remove that variability. And that's what the digital thread will bring to you. This is not something you're going to do in day one. You may not even have 3D models today that are fully defined to be able to bring a lot of the information. But even if all you have is 2D drawings and bills of materials, you can still get on the digital thread and start getting a lot of that continuity in place. This is not something you're going to do overnight, but this is something you should start doing immediately. So thank you very much for your time, and I'm going to turn the podium back to Paolo.